Hello, this is the genuinely approachable Sudoku for the 10th of March 2024. It is Palindrome by Clover featuring Palindrome Sudoku. So let's take a look at the rules. Normal Sudokus apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Digits along grey lines form palindromes, meaning that the sequence of digits on a grey line is the same in both directions. So for example, something that looks like 1, 2, 3, 4, 3, 2, 1, ignoring the red, is valid because reading in one direction is the same as reading in the other direction. And in fact, I'll just make this both 7s to say this is a valid palindrome because reading in one direction gives you the exact same sequence as reading in the opposite direction. So yes, those are all the rules. With that, let's just begin solving. Now, an interesting thing about palindromes is that digits on the same positions in both directions, so to speak, are the same digit. So for example, this is 1 from one end, while this is 1 from the other end. So they both have the same value. Similarly, this is 2 digits from one end, while this is 2 digits from the other end. So they must have the same value as well. So this is a 9, and similarly that is an 8. And well, the reason why is because if you read in one direction, 8 is going to be the second digit. So to read in the other direction, 8 must also be in the second digit. Yeah, and that's how it would work. We could probably also talk about those digits then. Well, not really. Although I can tell you that those digits are decently special because they each look at 6 different digits, you know, in a way of speaking, because those 2 digits are always going to be the same, because they are an equal distance from each end of the line. Therefore, this digit and that digit, for example, since they must be the same, if this digit cannot be 4, 5, and 6, then this digit also cannot be 4, 5, and 6. This digit can't be 1, 2, and 3, so this digit also can't be 1, 2, and 3. In total, those digits therefore cannot be 1, 2, 3, 4, 5, and 6. In addition, this digit can't be 8 or 9. So in fact, those digits can't be 1, 2, 3, 4, 5, 6, 8, or 9, they just have to be 7. Those digits also face a similar problem where they can't be 1, 2, 3, 4, 5, or 6. They also can't be 7 because we place them here. And in fact, because of this very interestingly placed 9, they can't be 9 either. So they are just 8. That is not something we can say here because 6s are repeated in here as well. Although in fact, we might still be able to do something interesting with these digits given we've placed other existing digits there already. For example, those digits are marked with orange. Actually, no, let's not mark with orange. Let's do those. It's easier to see this way. Yeah, this system of colors is easier to see. Those digits, for example, must be the same, but they cannot be any of those digits. Is this something we can use? Maybe it's this digit. Yeah, this one is something we could probably use. It cannot be 1. It cannot be 2 or 3. It can't be 5 or 6. It can't be 8. And it can't be 4, because 4 is in the same box as this cell. So it must be a 7, right? Because it can't be 1, 2, 3, 4, 5, 6, 8. Oh, it could be 9. Oh, but it can't be 9 because of the 9 in the box. So yes, it can't be 1, 2, 3, 5, 6, 7, 8, or 9. 5, 6, 8, or 9, so it has to be 7. Alright, that was explained pretty poorly, but hopefully it's understandable. This digit can't be 1, it could be 2 or 3, so immediately we already have at least 2 options here. It can't be 4, it could be 5, it can't be 6, 7, 8, or 9. So it could be 2, 3, or 5, which is a lot worse than the rest of the digits we've looked at before. That's okay. Where does 7 go in this box now? By regular Sudoku, we can place it here. Could probably do the same with the rest here. 7s, for example. Well, I guess 7 could be there and there. That is valid. And I will place a 7 in this box, but I think that's thinking a bit too far. Let's see. I suppose 6. 6 is one of those cells. And in fact, the 6 in this box is one of those cells. That's not very helpful. We want digits on palindrome lines. and not of them. I suppose those 2 digits might be useful. Are they useful? Those 2 digits must be in here somewhere. But they can't be. No, hold on, wait, I'm not looking at this right. Those digits must be in here somewhere, right? So whatever those digits are in one of those 4 cells. They can't be 8 though, because they already see 8 in the column and row. They can't be 6 either, because it sees 6 up here, which is very hard to spot, but there it is. And therefore must be in one of those cells. Is that useful? I think it might be a bit too much. In this box, they also have to be in one of those 4 cells. I don't really see how that's useful though, so no. I think more appropriately, yeah, what we just do is regular Sudoku. The 9s in this box must be here, meaning 6 goes down there, meaning 6 goes up here. Alright, that makes a lot more sense. Those digits have to be 4 and 5 to finish the box. That digit and that digit is the same, so that digit is also 4 or 5. This forms a triple of 1, 2, and 3. This digit is over here, which cannot be 3, so that it can only be 1 or 2. Cool. This also forms a triple. They have to be 2, 3, and 5. But none of them lie on palindromes, so that restriction doesn't exist. You could probably do Sudoku here though. Like, we do it with 9s here, but we could do it with 8s here maybe. 8s are in one of those cells. I guess unfortunately 8 could be there, which means that 8 could also be there as well. This does form a quadruple of sorts. I guess you can use that. Yeah, I guess where does 4 go in this box? 4 can't be in those cells, so 4 is in one of those cells. It could be there though, because 4 could in fact be there. There is no issue with that. 5? Well, yeah, I can see stuff. Where does 5 go in this row? 5 can't be there. 5 can't be there either, because that's the partner of that cell will be here, which already sees 5. So this can't be 5 either, meaning 5 is in one of those cells, forming a 5-8 pair. Those digits therefore form a 1-5 pair, which does remove some stuff here. This can't be 5. Whoa, hold on. I'm missing something. Wait, this is not 1-5 pair, it's a 1-4 pair. Whoopsies. So this digit is over here, so this is a 1 or a 4. More importantly, this 5-8 puts a 5-8 there. It also removes 5 from those cells, which forms a 2-3 pair. That digit is therefore just a 1, which means this is a 2, which means that is a 3, which means that is a 5. This 2, 3, 5 means that's 2. So that is a 2 over here because we know those digits are the same. That is therefore a 3. This 1 actually resolves this 1-4 pair, which I didn't notice before. And this 4 travels up here to push a 4 into that cell. Yeah. Okay, that's cool. Let's keep going. Those digits are 1 and 9. This one resolves that. Those digits are 2, 3, and 5. 5 come in those cells, so 5 goes down here. This forms a 2-3 pair, which means that digit is just a 9 to finish the box. Those digits are therefore 3 and 4 to finish the box. 5 makes that a 4, which resolves this 3-4 pair. This 4 also transfers all the way across the palindrome to that cell, so that's also a 4. Meaning 5 goes here. We could probably do stuff, could we? No, I don't think we can. I think we're basically done with all the palindromes now. This 2 means 1 goes there. Oh, sorry, 2 goes here. We can also tell because this 1 resolves that for us. We do know that those digits are the same, which we haven't used yet. So yeah, alright. Okay, let's do regular Sudoku. 9? No, 9 in this box goes in one of those cells. 4s, there we go. 4s in this box goes over here. They probably resolve everywhere else as well. Yep, 4s in this box go up here. That is all the 4s. We also have 9s maybe? Not really. 6s. I suppose 6s, yes, must be in those cells. Which means that in this box, 6s are in one of those cells. Okay, that is not as helpful as I thought it would be. Although I can place 6 in one of those cells, and that is because 6 cannot be here, because this digit cannot be 6. So because 6 can't be in those cells, 6 is in one of those cells. Wherever those cells are, they will see those cells. This 6 also sees those cells, so 6 is now in one of those cells. This 6 resolves that, which pushes a 6 into this cell over here. That's very nice. It's a roundabout, a very roundabout piece of logic, which is cool. This is 2, 3, and 7. This digit can be 2 or 3, so it's 7. This 2 resolves the remaining 2, 3 pair that forms. And I suppose those digits form a triple of 1, 5, and 9. 9 can't be there, but 9 can be anywhere else. Okay, this also forms a triple. They have to be 3, 7, 9. That digit therefore is the same as that, so that digit is a 3, 7, or 9. However, because of the 3, 9 pair here, that digit cannot be 3 or 7. 3 or 9, it must be 7. This digit now can't be 7. Same for that digit. Is anything resolved? No. Okay, the last digit we haven't seen here is an 8, which is one of those cells. I don't see anything to do with that though. Yeah, nothing much. I suppose an interesting little gimmick here is that 8 is always in one of those cells. It's a bit harder to prove, but you can say that. I'm not going to try to prove it this time though. Let's look at other stuff. 3s, for example. Not very useful. I don't know why I'm taking so much time with this. Shouldn't be that hard. Those digits are 3, 6, and 5. This can't be 6. That can't be 3. This could be anything. Okay, those digits form a triple. They have to be 5, 8, and 9. This digit can't be 5. That digit can't be 8. Oh, that forms a chocolate teapot. That is very satisfying, of course. Of course it's satisfying. Okay. I have a feeling it's those 2 digits that require some resolution, because I haven't figured them out yet. I don't want to go through the can it be 1, can it be 2, can it be 3 sort of trick, because we already used them for the colored cells. There must be some more elegant way to solve this one. Like how both of them look at all of those cells here, because they are the same. Therefore, they must be from this subset of cells. Similarly, they look at those cells here, therefore must be a subset of those cells. Does this do anything for us? Probably not. I suppose because 6 is one of those cells, they can't be 6. They definitely can't be 7 either. I should not highlight all the 7s. But they definitely can't be 7 either. So they come from up there. Which, again, we don't know because that has a lot of options. I suppose that they are therefore either 1, 3, 5, or 9. The 3 and the 9 here remove 3 and 9 from those cells. But I don't see anything else that does, except this 1, 5 here forms a pair. That is pretty weird. I don't think it's very elegant, but there it is. So that must be an 8 from the 8, 5 pair. This 8, 5 pair resolves this 8, 5 pair down here, which resolves the 1, 5 up there that we just used. The 5 here also makes that a 3, which probably does something. This now can't be a 3. So 3 in this box, yes. 3 can't be there, so 3 must not be here. 3 can't be there, so that's a 9. 3 in the corner, very nice. 9 means that is not a 9. 5 means that it's just a 1. That is therefore a 9 to finish the column. This is a 1, 5, 6 triple, which means a chocolate teapot. Definitely very useful. Okay, what else do we have? This and this form a 2, 3 pair. 8 is not there anymore, so 8 goes up here. In fact, the 2 here just resolves the 2, 3 pair that we were just talking about. Those digits are 5 and 2, which is resolvable. Those digits are 7 and 8, I believe. Yes, and this 8 resolves that. 7, 8. 8 resolves this final 9, which gives us a 5 here and a 6 there, which resolves this 5, 1, 5, 6 triple, and the last 2 digits are 1 and 2. That is easily resolvable, solving the puzzle in 14 minutes and 20 seconds. Alright, we took a roughly slower approach to this today. Slower. But alright, no worries, this was still very fun. I hope you enjoyed this video. I'll see you guys next time. Bye bye.